Okay, I think we're good to go. Yes, we are. YouTube is always so slow. Excuse me. Okay. I don't know how much cleanup I did on Sunday. I just realized something as I was looking at the renderer just now. Well, just before the start. And what did I notice again? Oh yeah, here. This needs to be pointed to memory. Why did I have to make it so complicated? That means I didn't have to change this at all. So if I change this back to a slice. Oh no, because I know why. I'd have to allocate each of those slices individually, as far as I understand, which I don't want to do. Is that how it's actually done? See, alloc 2D array. And then with a for, allocate memory for each element. Okay. Int star array of m equals malloc size of int and m. Array is the pointer to int m. Is like oh, so the one inside. Oh, but what about the rest? Okay, so how do you allocate to the array? Sick. It's just not a big. What about a normal 2D array? Feels like there might be a simpler way to do this. Mem dot edit list. So mem, not sure. standard.added list. Guide added list. So I'm guessing this can be a slice of U8. How would they in it? In the right file. Oh, that's fine. I was looking to see if I could look at the implementation. Alright, never mind. Testing changes to input recording. Input aside firing and turning off topmost window. Yeah, I'd like to see this.
All right, so this is one that is kind of interesting to try. Per Vonson wrote this in, actually. He's a person I actually know personally. He used to work at Rad Game Tools. I believe he is at Oculus now. But basically, he was suggesting to try something which I think is pretty interesting, and it may work. I don't know. I don't think I've ever tried this before. But basically what he was saying was that, and I may be putting words in his mouth there because he tweeted it to me, so of course with 140 characters, sometimes it's hard to know. But basically, when we go to write out our recording, when we do our recording and we want to blast out that huge memory buffer, like a lot of it's zeros if it hasn't been used yet. And so one of the things that he was pointing out is you might be able to use NTFS's sparse file information to make that write faster in the cases, for free basically, in the cases where there isn't that much stuff in it. Now, I don't think this will help us at all in the case when we actually have the full running game, so this may be kind of a hollow victory in some sense, but for the time being it may help us because, yeah, it may help us make the write faster in cases where we don't have where we don't have stuff it actually filling the memory buffer. So basically, device I/O control is a thing that sort of tells Windows additional information about handles and how you want them to work. So we have a handle to a file here that we created, and we can give it some information about how we expect writes to happen to that file. And so the thing that we want to do is this device I/O control call. We want to do that after this. And the thing that we want to look at is this thing. It's a bit weird. It's called fctl set. What was it? Set sparse, I think. Set sparse. This guy. So, oh, they've already filled out the whole thing for me. That's even easier. So, okay, that's basically what that is the call that we want to do. And so what this does is it says that a particular file is allowed to be stored, or that Windows can look to see if large ranges of the file are 0. And if they don't need to be stored, then they just won't be stored. So since we know that almost all of our memory is 0 right now, it might be that that helps Windows do this operation a lot more quickly, right? So basically all we'd be doing here is just calling this device I/O control purely as a hint to Windows, basically, saying, hey, we've got this handle, right? We want to set it to sparse. I don't know what the input buffer part is. Let's see. a pointer to the sparse length, so the parameter is optional and commits to null. So we don't care about that. We're not going to set that at all. And the in buffer size will also be 0. The output buffer will be 0. That will be 0. Bytes returned. That
Not
can be
sure I
null as well.
understand. What's the point? Excuse me. Just to get the recording handle. Begin recording input. Let's write the giant memory block and use memory copy instead. How do I write? I don't think that's how I do it at all. Record. So if it's recording, what does it do? Or I just write per input. Maybe that's not a good idea. I mean, but it seems to be pretty fast. MS bytes. Because I can sort of still keep sig fill. Oh. I didn't know it was broken. What did I change? Following command exited with edit code 1. Why are you exiting? Oh, I did change the path. So it was working fine yesterday. Oh, because I know why. Okay, that's the added turn. Build failed. I think I added some args. Big build. Lib. Save my comment. Chocolate run, zig, build lib. What is game code? So slash handmade.zig. Dynamic. Okay, there's only one. Put this back. Okay. Why did I? Oh yeah, because I wanted to check the FPS. If I start recording, doesn't really affect the FPS. Maybe I should increase the FPS. Target FPS. Maybe higher. Where's fucking 6? Here. And if I start recording, I mean, it's still, considering OBS is running. Something weird happens with the input. What is the playback so fast? Oh, because I know why. Playback. I think I might have hard coded the. Interesting. I think I should also just read the whole thing. Then here, write larger chunks of inputs at once instead of increase one at a time. See what happens if I put it to 120. Index out of bounds. Oh, I know why. No, I don't know why. Is that the only thing I changed? Blend 735. Index 735, blend 35. What is 735? Yeah, it's a problem for later. But what I think is thread I wonder if there's a thread limit. Like there's a limit to how many in the pool. Say thread pool. That is my first guess. So I'm guessing what are the args? Oh, these are the argument for the function. That's the first thing that comes to mind, really. Better way to see how many threads per pool. Yeah, thread count. Options dot and jobs. Oh, it's CPU count. That makes sense. I don't think I have that many CPUs. No, but 735 is still good. I think it's the audio. This breaks at 120 FPS. Work for Wire. Yes. I might have to figure out another way to write audio. Maybe even use... But actually, to be fair, I don't care much about audio. Alright. Looking for improvements. Yeah, actually, this is something I want to check too.
Well, I will say that there's a virtual alloc thing that I thought might be good to do just for fun, which is that to relieve some pressure on the translation look-aside buffer potentially, which is something we haven't gotten to yet. But one of the things that we could do is in our giant virtual alloc that we do down here, this guy, where is he? Oops, virtual alloc. I was almost there. There we go. So in this guy where we do our giant virtual alloc, it might be nice to allow the operating system to use large pages. And so the way that this works is, excuse me, I believe, yeah, so there's this guy here, large pages. What large pages are is when you do this mapping, when we're talking about virtual memory, right? We've got our application space is laid out in these pages, right? We've got page size, and that page size I think I was talking about before is usually 4K, so it's 4096 bytes. And basically, what has to happen is inside the processor, right? Because remember, in fact, let's just do. You know what? Since this is the Q&A, since we're starting the Q&A now, let me just do a diagram here that explains this, what's going to happen, because it's something that's useful to know. So let's just use the first part of the Q&A for that. So okay, let's go over this one more time. Here is physical memory, right? So this is physical RAM. It's the actual RAM on your computer. So I don't know how much you've got. Let's say it's a pretty good machine. It's 16 gigabytes, right? So basically there's 16 gigs of physical memory in the machine. It is actually laid out in order. It goes from byte 0 to byte 16 gigs, right? And it's all there. Now, in our process, we have process virtual memory, and that virtual memory is some other thing. It has no relationship, really, to this physical RAM, right? So we see, byte 0 is, that's a great arrow. We see byte 0 is here, and I don't know, we allocate, who knows how much we have, but we're looking at memory just kind of going up, and this can go all the way up, I believe, to 8 terabytes in 64-bit Windows for the app, and then I think there's another 8 terabytes for the system. I don't actually remember, so I don't know if that's true. But basically, there's 8 terabytes. This is, again, the worst diagrams today. Let's try that again. 8 terabytes for us, and 8 terabytes for the system, so that's like a 16 terabyte thing. I think it looks something like that, but I don't actually know. I think there might be a bunch of space in between here. I'm not sure exactly what this looks like. But point being, this is some totally other space. This is no bearing on physical RAM. We may look at something and say, oh, and in fact, we did, when we did our virtual alloc, right, we asked for it to be at this base address, right? And the base address was at 2 terabytes. So we actually said, oh, okay, the base address is somewhere like right here at 2 terabytes. Well, 2 terabytes, there's only 16 gigabytes in the machine. 2 terabytes is way off the end of physical memory if you think about where it actually is located. So this is a purely fictional address that we've created. And so our game exists in 1 gigabyte of memory right here or whatever. It's a little more than that because we have 64 megs of perm store or whatever. But like we said at the 2 terabyte range, we're going to use the number 2 terabytes, and all the bytes in between there and 1 gig from there are going to be part of our game. Those numbers have to correspond to something in here when the processor is actually doing work, right? So the CPU is sitting here running our game. It's going to see a number that looks like 2 terabytes. So 2 terabyte number, the number 2 terabytes, whatever it is, some number, it's actually some big number that's like complicated and long, right? 2 terabytes with some fractional part or whatever, right? So some crazy long byte address. And in fact, I can even make this more concrete, right? Let's go in and just see one of the numbers. I can give you an example of exactly what it is. Inside our game, let's see here. Let's take a look. So we go into our game call, which I need to put some comments in here soon so I can find my way around. I keep getting lost in my own code because I haven't made any markers in it. What's going on? Why can't I set a breakpoint? Recompile. Run. There we go. Okay. So inside here, here's game update and render, right? So let's just take a look at what the pointer to, like, say, the player X. Where is player X being stored in memory, right? Well, there's the number. And you can see there's that 2 terabyte or whatever, and there's the, like, fractional part of it, the offset from there, right? So that's the number. And if you actually look at what this equals in a decimal, right? Let me try and cast that to a decimal. I don't know if it'll actually do it or not. It does not appear to actually do it. Why won't you convert it? There it is. So I guess I don't know my way around the Visual Studio watch window comma syntax very well, but if you put a comma after something, then there's these codes you can use in Visual Studio that will turn it into different number types. So like .b is binary. That's a new one that that didn't used to work, but that works now. D is decimal. So you can see this is actually the number. This is the number that the processor actually sees. When we go to reference player X, the processor sees this number, right? So that number is coming into the CPU here, right? It's the CPU is seeing that crazy number we just said. Now, that number doesn't exist. That location in physical RAM does not exist. There aren't 2 terabytes of memory even in the machine, let alone 2 terabytes plus whatever that was, plus some, where we were looking at. It would be way, way off the end of physical memory. So what has to happen is the CPU has to translate that address into wherever the memory is actually being stored in physical RAM, which the operating system manages. It basically pulls in parts of the memory that we ask for and keeps them in physical RAM as necessary, and it can do stuff like swap them out to disk if it needs to, right? There's a paging file, right? It can swap pieces out to disk if it runs out of physical RAM. Storing stuff, it can move it out to disk. And in fact, you can see it move it out to disk. If you actually look, I think you can see it here. Let's see if I can see it here. So yeah, you can see on the C drive, there it is right there, pagefile.sys. So if I do pagefile.sys and do a dir on that, well, all right, so it won't let me dir it because it's some operating system protected file nonsense, I guess. But you can see it there. That pagefile.sys is actually where it's writing the stuff that gets swapped out. So in this process, what has to happen is there has to be a way for the CPU to translate those addresses. It has to do work to support virtual memory. Virtual memory isn't free. The CPU has to actually dedicate circuitry for doing this process. So how does it translate that number? Well, the way that it does that is in chunks. Basically, each 4K page, right, so 4,096 bytes worth of memory, each 4K page basically is mapped individually between virtual memory and physical memory, such that there is a page table which literally says stuff like, okay, you can imagine something like there's the physical address and the virtual address, right? And they're mapped in like a table. So we basically say, oh, physical address, 16 or something maps to virtual address, 2048 or whatever, right? It's basically just a thing that says the 4K based at this address, well, these would all be on 4K boundaries, obviously, so those are stupid examples. But like the physical at 2 times 4096 and the virtual at 10 times 4096 are the same page. We have mapped this location to this location, right? And what you have to appreciate is that this mapping isn't free. It has to actually be stored and it has to actually be managed. So the CPU has a bunch of stuff in it to try and make this faster. And one of the things that it has is something called a TLB, or translation look-aside buffer. And basically what that is something designed to translate addresses quickly by having a small number of these mappings directly on the CPU that can be looked up extremely quickly. It's basically like a cache for address translation, right? And you can look this up if you want more information. I'm not a CPU guy, so I'm not the guy to give you the explanation on that. But you can look for this translation look-aside buffer. You can look for this on like Wikipedia, and it can sort of tell you, right? So it's cache for virtual addresses, like I was saying.
I think there's like a better resource for what every programmer should memory. Did this one? I think so. I read it a long while ago. I don't know if... Can you search this? Oh yeah, here. TLB. Optimize TLB usage. Translation look aside. Here. Where does it start? Optimizing page tables. Oh, here we go. I think this is what he's talking about. Did I read this bit? I think so, yeah. That was a long time ago. Might go back and read this again. Maybe just the virtual memory stuff. I remember parts of it, not all of it though. Maybe I can just leave it in the... I'll leave it somewhere. But I guess it's easier to find. Optimizing page table access. All data structures for the page table are kept in main memory. This is where OS constructs and updates the tables. Oh geez, it's quite bad. Where did it go? Yeah, here. Page tables are used to resolve every virtual address into a physical address using the page table walk described above. Virtual address. It's a directory and an offset. The interesting part is the translation of the virtual address to physical address. The MMU can remap address on a page-by-page basis. Just as when addressing cache lines, the virtual address is split into distinct parts. These parts are used to index into various tables, which are used in the construction of final physical address. With simplest model, we have two levels of tables. It's a page directory. So is this like a page or is a table? So this will be like 4K, I'm guessing. The top part is used to select an entry in a page directory. Oh, okay, I get it. Well, kinda. and the offset points to the physical address. Each entry in the directory can be individually set by the OS. The page directory determines the address of a physical memory page. More than one entry in the page directory can point to the same physical address. Yes, if the offset can. More than one entry in the page directory can point to the same physical address. The complete physical address of the memory cell is determined by combining the page address from the page directory with the low bits from the virtual address. Determined by combining the page address from the page directory with the low bits from the virtual address. Okay, combination of page address and the offset. Page directory also contains some additional information about the page, such as access permission. The data structure of the page directory is stored in main memory. The OS has to allocate contiguous physical memory and store the base address of this memory region in a special register. The appropriate bits of the virtual address are then used as index into the page directory, which is actually an array of directory entries. Okay. Appropriate bits of the virtual address are used to index the page directory, which is actually an array of directory entries. Okay. So there's an array of page directories, and then somehow eventually they are translated to a physical page. For a concrete example, okay, this is good. This is a layout used for 4 MB pages on x86 machines. The offset part of the virtual address is 22 bits in size. 4 MB pages on x86. The offset is 22 bits, enough to address every byte in the 4 MB page. The remaining 10 bits of the virtual address select one of the 1024 entries in the page directory. I'm going to read that again. The offset part of the virtual address is 22 bits in size. Okay, yeah, because 32-bit memory. And the remaining 10, the virtual address, select one of the 1024 entries in the page directory. Okay. Each entry contains 10-bit base address of 4 MB page. Ten-bit base address of 4 MB page, which is combined with the offset to form a complete 32-bit address. Well, I get parts of it, not all of it. How do you optimizing page tables? All the data structures for the page tables are kept in main memory. This is where the OS constructs and updates the tables. Upon creation of process or a change of a page table, the CPU is notified. The page tables are used to resolve every virtual address into physical address using the page table walk described above. More to the point, at least one directory for each level is used in the process of resolving a virtual address. At least one directory for each level is used to process in the process of resolving a virtual address. Yes, because you'd have to walk through the array of directories. This requires up to 4 memory access for a single access by the running process, which is slow. It's possible to treat these directory table entries as normal data and cache them in L1, L2, etc. But this would be far too slow. Different optimization is simple. Computation can show that only keeping the directory table entries in the L1D and higher cache would lead to horrible performance. Each absolute address computation would require a number of L1D access corresponding to the page table depth. Yep. These access cannot be parallelized since they depend on the previous. Yes, exactly. This alone would on a machine with 4 page table levels require at least 12 cycles. And the probability of an L1D miss and the result is nothing the instruction pipeline can hide. The additional L1D access also steal precious bandwidth from the cache. So instead of just caching the directory table entries, the complete computation of the address of the physical page is cached. Ah, okay, so that's what this is for. This is what Casey talking about, I guess, but not that I understand all of it. The cache into which the computer values are stored is called the translation look-aside buffer. It's usually a small cache since it has to be extremely fast. One CPUs provide multi-level TLB caches just as for the other caches. The higher level caches are larger and slower. The small size of the L1 TLB is often made up by making the cache fully associative. Then allow you eviction policy. Okay, not that I mean, I don't remember any of this, although I read the whole thing a long time ago. TLB is a processor core global resource. All threads and processes executed on the processor core use the same TLB. Since the translation of virtual to physical address depends on which table tree is installed, the CPU cannot blindly reuse the cached entries if the page table is changed. Interesting. Each process has a different page table tree. Anywho.
And it can kind of explain to you a little bit more about exactly how it works. But the part that I'm trying to get to that I thought was interesting to kind of dive into here, and the reason I wanted to talk about it, was because if you think about what happens, the number of entries in this table, the number of entries in the number of total entries of translation that have to happen in the operating system, right, is based on how big this number is. If each thing is 4K, then there's going to be a certain number of entries. If everything was instead 16K, right, then there would be 4 times less entries. Because for the same amount of memory to be mapped, each mapping stores 4 times the amount of addresses, essentially, right? Because you're mapping it in 16K blocks. Which means that for a translation look-aside buffer on the CPU, if the pages are 4K, there's going to be a lot more entries in here than if they were larger.
Right.
And so what I believe is that I believe you can switch to using 2 megabyte, which is massively larger than 4K. I believe you can switch to using 2 megabyte sizes for the translation look-aside buffer. I don't actually know if that's true, but I think that's something like that is basically true.
I think there was mention of 4 MB, yeah. But I don't know if that's the physical page. Where was it? Table with 2 by 20 entries is not practical. Even if each entry would be 4 bytes, the table would be 4 MB in size. Okay, that's the table. Four MB pages on x86 machines. The offset part of the virtual, yeah, this. So it does mention a 4 MB page. But I don't know what's actually possible.
And if you tell virtual alloc that you're okay using large pages on some operating systems, on some versions of Windows, I think it can actually switch your process to using 2 MB pages, which takes a lot of pressure off of that TLB. And so since we're allocating one big chunk, it may be that we can get a lot of benefit there and take pressure off of the CPU by doing that. So it's just something that I wanted to mention. And so I think it's probably worth us passing that flag in the case that we're not on Windows XP.
Why did I allocate? Oh, it's just 1 GB. Thought it was 1 TB. Oh, that's why it's wrong. So that was supposed to be the address. I think in the arena allocator you can. Oh, jeez. It's too much. Child allocator. What is a child allocator? Sysmem.allocator. Keep the page allocator. Root name OS has the evolution root to the OS and page allocator. Can you specify page size? Don't think they mentioned it here. I've read this.
To just say, hey, let's go ahead and use those large pages. So what I want to do is I just want to go ahead and pass that. That's about it. I believe that's on. That's
Take virtual. Let's just reassign 0 and 1. Each time we allocate, we must call virtual alloc with that size. Let's assume we are not going to exceed 64 kilobytes. That means that we need 16 pages and 16 virtual and physical mapping descriptors. Is it limited to 4 kilobytes in the physical memory? I think this is Casey's video.
On the mem commit mem reserve whatever side of things, so it's right in here. We do that, and I'm just going to put to do in there. To do like, do we need to not pass out an NT? Will that mess up NT? So do we need to not pass mem large pages on Windows XP, or will it be fine? Right, that's about it. So I just wanted to try that because I think that may help us in the future basically avoid the situation where we have a lot of TLB pressure. That's just another thing that can make life harder for the processor when it's trying to run our code. So I'm just going to see if that works. All right, so that doesn't work. I assume there's a problem with allocating the mem large pages that way. I don't actually know what it is, but I'm going to take a, sorry to eat up Q&A time. We can go a little long, but I just wanted to try that because I've never used it before, but I feel like it's something that we could do. So I'm going to see if there's anything particular that we have to do. To use large pages, sorry, lock memory privilege by calling just tokens. So we didn't do that. We'd have to do that. Retrieve the minimum large page size, include minimum large pages. So we'd also have to do a little bit extra, it looks like here. We'd have to actually call adjust token privileges to basically say, hey, we're going to be a large page app. All right, so maybe I'll have to leave this as a to-do for later on in things, because that does actually sound like, I was hoping we could just say, hey, please let us use large pages, but it doesn't look that way. So let's see. Use mem large pages and call adjust token privileges when not on Windows XP. So that's something that I'd like to do in the future, because the translation look-aside buffer actually can cause you to slow down, because basically anytime you miss that translation look-aside buffer and you're accessing an address that needs to get translated and you have to pull new entries into the TLB, that's another source of processor slowdown, right? And so since we don't really care too much about how that memory is paged because we're trying to run in all of our game in memory at once, I feel like there isn't probably much of a downside to using the large pages. Maybe that's not true, but I would at least like to have it in our app so we could do some testing and like turn it on and off and see if it made a difference in any way. And it might be that we find that it just doesn't matter, but since we can do it, I thought it might be nice to try. All right, so I think that's about it.
That does remind me. I need to fix my allocations. To do. This could be done better. Not sure yet, but I think it can be done better. Would be nice to just allocate. Like, I don't use this at all. I do allocate transient storage, but I understand it's for like later. But I could do something similar. Just allocate all of this together and just use as much as I need. Could be possible though. For instance, yeah. So let's say we have game state, memory, screen buffer, then we have the audio buffer. In fact, this could be before. So I guess allocate, let's call it total mem equals total mem, and then game state contact would be 0 to size of game state. Same for total mem, and then the audio buffer. That makes more sense. So I don't have to like allocate individually. Let's do it once and then use part of it, because I know how much memory is required. The question is, what is size of struct? And let's say buffer of is the size of, let's say, the memory part of it, part of the struct. That would be the question. But no, actually, because it's a pointer, it would just be size of pointer. Yeah, okay, it's asked and answered. I could do something like that. And then game state dot audio would point to this actually. I think this won't be 0. It would be size of game state. Something like that. The other thing is I would need assertion assert reads, because otherwise I could potentially read outside of the memory. Yeah, leave that in there. I think this also sounds like fun. Okay, I think that's it. That's the last part. As for tomorrow, getting the actual, oh yes, there's a few to-dos. I think the monitor refresh rate. and getting the current monitor. Pairing for multi-threading. Okay. I think I did. I used the thread pool. But there is a problem with the audio, because if the buffer gets too small, if the frame rates go high, I don't know, the audio needs fixing, if anything. Getting state of the mouse buttons, oh yeah, good point. Making improvements to replay code. I think the mouse is easy. X11 mouse. Oh. I think get mouse input. Index. Yep, this one. How can I go to play functions, window, color, input, device functions. Grab the point to use. I don't think that's it. Is it? X keep, I forgot what it was called. Key press. There we go. Is this mouse? What was the event that you had to key press mask? Select input. Client is interested in. Where's the list of? Oh yeah, here. Key press, key release, button press, button release, pointer motion, button motion. Okay, you can just set it to all events are propagated by setting. Okay, so you don't want them to propagate. So I guess it's one of these. I'll have a look at it tomorrow. Some cleanup done. Not required. Okay, I think I'm gonna call it a day there. Should really save and save this. Yeah. So always have to like always forget. Okay. I'm gonna call it a day there. Thank you for hanging out, as always. It was kind of a slow stream. Nothing much needed to be done. Alright, hope you have a good one. I shall see you back tomorrow. See ya.